there is a quiz posted about the previous two lectures together. Yeah, that is light quiz 1, and there was some trouble I think regarding the deadlines, so I have extended it to further in the evening. You can see the eLearn portal for the exact time of the due date. Okay, so you need to finish that. That is one thing. Secondly, I have also scheduled a office hours. Yeah. So the plan is we will have 3 office hours in a week. And we have 3 lectures in a week, and the other 3 days we will schedule office hours in the evening. Okay. So I think the office hours has been scheduled at 5 o'clock or something like that. So please contact the TAs or put a message in the Teams if you have any problems with it, or yeah, if you want to reschedule it or something. Okay, so let's get started with today's class. So today's lecture is going to be on conditional probabilities and independence. So let's just start reviewing what we did previously. So we saw, okay, yeah, if you want to start learning probability, you need to understand first the sample space. Sample space is a set of all possibilities, yeah, and so please go through the teams. There is a general channel, there is an announcement channel, and if you go through it, you will see that it has been scheduled in your calendar. Yeah. So please use the Teams general channel if you want to look at the office hours. Office hours is for clearing doubts, if that's the question. Okay. So yeah. So sample space, we saw what it is. We also saw what are the axioms of probability, which is yeah, probabilities of any event has to be positive, and the probability of the sample space has to be equal to 1. And for disjoint events, the probabilities add up. Yeah. We also saw a case when you have infinite sample spaces, we need to be a little more careful. Yeah. So yeah, we spent one entire lecture on it, on infinite sample spaces. Okay. So we also extended this this condition to countable additivity. Okay. So you can add up probabilities when you're adding up only countable number of things you can add up, and these events has to be disjoint. Then you can add up, and uncountable number of events you cannot add up. Yeah, that is very important. And we saw paradoxes that can occur if you do that. Yeah. Then yeah, we also solved few problems. Yeah. And yeah, whenever you try to attack a problem in probability, you need to first find out the sample space, yeah, and understand the probability laws. Yeah, what are the probability in the sample space in the atomic events? And before trying to solve the problem, understand whether how to attack the problem. Maybe the complement is easier to calculate. Maybe you can decompose the problem into some sub events, okay, which whose union is the full event, and you can compute it individually. Yeah. So yeah, the initial tricks. So you could use all your set theory, Venn diagram knowledge for doing this. Yeah. So today we will introduce a newer trick that is used for computing probabilities. It is called conditional probability. Okay. So yeah, so this is one of the common examples that you see when you teach computer, whenever you talk about conditional probability. So just a second. Yeah. So there's this game show. It was called Monty Python or something like that, and so there is a goat, and there are 2 goats and 1 car. Okay, and initially these are randomly assigned behind 3 doors. Yeah. And the host of the show actually asks a participant to ask which door to open. Now, yeah, he will say some door. Yeah. but there is the other two doors which the participant hasn't selected. The host knows what is assigned behind which door. Okay, so he will open that door where the goat is there in the other two doors. Okay, so there is 1, 2, 3, and let's say I am the participant and I selected 1. Okay, the host knows what is behind the other two doors. So the one of that has to be a goat, and he will open the door corresponding to the goat. Now the question is he will then give the participant the option whether to change his option or not. Yeah, and whether you have to stay with your choice or you change your choice. You have two options. Yeah. So which option should you choose? That was the question. Yeah. And so question is like, how do you analyze this probability? So we need to have a way of mathematical way of always change. Okay, but how do you justify it mathematically? Why should you always change? What is the justification for it? Yeah, there should be some reasoning for it. No. Okay, so what is the reasoning behind? Okay, yeah, probability, but what probability? We need to understand how do you say that changing is better than sticking with the first choice? Yeah, so that is what we are going to talk about in this lecture. Okay, so yeah, this is called conditional probability. So yeah, as the earlier problem, so sometimes you are given some extra information about the problem. There is some probability space, there is some sample space probabilities are distributed, and then later somebody gives you some extra information. So here the host gives you this information that this one particular door is actually the goat. Yeah. Now, now we want to analyze the probability of whether to stick with your first option or the change your option. Okay, and we want to analyze this, and that's what conditional probabilities are about. So let's look at familiar examples that we looked at from earlier. So you are rolling 2 dice, and 6-sided dice you are rolling. Now, what is the probability that the sum of the numbers is 8? That is a good question. Yeah. So how many possibilities are there? So there are, there is dice. Yeah, so there are 6 possibilities here, 6 possibilities here. And how many possibilities you will get sum up to 8? So yeah, if you want to sum up to 8, you can get if the one dice is 1, then we cannot hope to do much, right? You cannot ever get 8. But if one dice is 2 and the second dice is 6, it is fine. One dice is 3, the second dice is 5, again you will get 8. So the first dice is 4, second dice is 4, you will get 8. The first dice is 6, second dice is 2, you will get 8. Yeah. So did I miss out something? 2, 6, 3, 5, 4, 4.
5, 3.
5, 3.
Yeah, 5, 3 is also there. You are right. Yeah. Yeah. So there are 5 possible cases, and so initially the probability is 5 by 8, 5 by 36. Yeah, so there are 36 possibilities. Yeah. So that is the initial answer. But what if we know that the first die is 5? Somebody later told you the first die is actually 5. Okay. So now what is the probability of the same event? So if you know that the first die is 5, then there are only 2 possibilities here. Yeah, so there are only 2 possibilities here. But it's also important that now you know that the first die was a 5. So you're kind of restricting to to some subset of the sample space. So you had the earlier sample space which was 36 in size. Yeah. And now you're told that the events experiment happened such that only some 6 are remaining. You are told that okay, it is within the 6. So within the 6 there are only yeah. So Yeah, so you are told that the first die is 5, then there are only one choice. Yeah, so now the probability is only 1 by 6. Yeah, so yeah, so the probabilities change. Yeah, looks like the sample space also kind of changed from 36 to 6 when you are given more information. Yeah. So how do you talk about the probabilities when you are given this information and you are not given this information? What is the relations between them? Okay, so how to mathematically express these things, and yeah, that's what we are going to talk about. Okay, so yeah, this is the formula of conditional probability. So the probability of A given B is probability of A intersection B by probability of B. Okay, and what does this mean? So you earlier had some experiment and you had some probabilities for A and B and everything, but then you are given this information. Okay, okay, the first die is 5. Okay, so that is your event B. You're given this information that B actually happened. Yeah, and then how does it affect the probability of A? Yeah, so that's the probability of A given B, and the formula for obtaining it is just we saw. First, you need to look at the probability of B. So earlier in the dice case, the probability of B was 6 by 36. Yeah, in the earlier example, probability of B was 6 by 36. And yeah, so the probability of A intersection B was, in the earlier example,
1 by 36.
it was 1 by 36. So then so now probability of A given B, yeah, now 1 by 36 and 6 by 36. So it is 1 by 6. Yeah. So 36 nicely cancels. Okay. So yeah, so this is just what we said earlier, but now we have a formula for it. But the very important thing that you should be careful whenever you have something like this is this only makes sense when probability of B is not equal to 0. This is extremely important. So before you condition on some event, make sure that's a non-zero probability event. Otherwise, your conditional probability will not make sense and your calculation will completely go wrong. Okay. Yeah. So before you compute conditional probability, we need to compute the probability of B not equal to 0. That we need to ensure that the probability of B is not equal to 0. Okay. So yeah, this is another example. Like there are 3 coin tosses, and B is the probability that the first coin turned heads. Yeah. So 3 coin tosses. B is first coin is heads. Yeah, and A is the event that let's say all are heads. Yeah. So yeah, probability of A intersection B happens to be equal to probability of A. So yeah, it is going to be 1 by 4. Yeah. So A is actually a subset of B actually, so that becomes probability of A by probability of B, which becomes 1 by 4. Yeah, and the 8 nicely cancels. Okay, so it's actually 1 by 8 divided by 4 by 8, and the 8 nicely cancels. Okay, so yeah, so now let's solve some problems so that everybody understood this. People should be able to solve this problem. Okay, yeah. So you are tossing a coin 4 times. Yeah. So what is the sample space?
To the power 4.
The size of the sample space is 2 to the power 4. The sample spaces, let's say, you can think of it as binary sequences, right? So you will have a 0, 0, 0 all the way to 1, 1, 1. Yeah. So this is the sample space. Size of the sample space is 2 to the power 4. Okay, there's a difference between size of the sample space and what the sample space is. Okay, so we have the sample space. Now, what is the event A? Okay, so event A is at least 3 heads. So, what is the probability of A? So, how many occurrences are there where there are at least 3 heads? Yeah, how do you compute it?
4C3 plus
4C3
4C4.
plus 1.
Okay, so yeah, so I can choose the 3 positions where yeah, I mean where I wanted the heads to happen, right? And yeah, it is always everything is equally likely plus 4C4 into 1 by 2 raised to 4. Yeah. So yeah, I mean yeah, I mean this is essentially two. Another way of thinking it is 2 raised to 4 is the number of possibilities, and the number of binary sequences which has at least 3 ones is going to be 4C3 plus 4C4, yeah, which is 4 plus 1, which is 5. Is that clear? So what about the probability of B? Okay, first dose is tails. It's actually pretty simple. It is 1 by 2. Right?
Yes, sir. 1
Yeah.
by 2.
Now, what is the probability of A given B? Okay, let's yeah, just use the formula probability of A intersection B by probability of B. So, what is the probability of A intersection B? So there are at least 3 heads. So yeah, what are these 5 possibilities? Uh, so okay, so B is first toss is tails, right? So first toss is tails. That means it's a 0 star. So it is all the sequences which looks like this. Yeah, that is what B is. Yeah, and yeah, I mean, how many events of yeah, how many elements of A are in, also looking like this?
3.
So just 1.
So at least 3 heads. So only one. So
Yes.
only cases when these 3 things happen. Yeah. So I mean A intersection B is a set of size 1. Yeah. And B is a set of size 5. 1 by 8 is the answer. Okay. Why is 1 by 8 the answer? Okay. Yeah. Why is 1 by 8 the answer? Sorry, I think I confused a bit. Did I confuse? Yeah, sorry. Probability of A given B. I think I did the other way around. So A intersection B is 1. That is right. And the probability of B. So there are 8 possibilities. You're right. And yeah. Yeah. Thank you. Okay. So the number of possibilities is only this, and the number of possibilities in B, which is 8. Okay. So that is right. Okay, so that is good. So what about this? So I want everybody to do the second part yourself. Yeah, now, yeah, at least, so when you do probability of B given A, yeah, again there is probability of A intersection B by probability of A. And A intersection B is, yeah, we already said that the size of that set is 1, right? It will be 1 by 2 raised to 4 to be correct. And what about how many possibilities are there in A? There are only 5. So it is 1 by 5. Okay. So yeah, is that fine? So we are just applying the formulas or thinking about it conceptually. Okay. So yeah, I want you to be familiar with both the ways. Okay, so yeah, so once you define this conditional probability, so then you can, I mean, yeah, you can just rearrange the formula and then you'll get another formula for A intersection B. Yeah, so the probability of A intersection B is probability of A given B into probability of B. I'm just rearranging the formula. Now, this actually gives you a way of inverting the conditioning. So, probability of A intersection B is equal to probability of A given B into probability of B. Fine, this you know. But A intersection B is same as B intersection A. So, you can also write this as B given A into probability of A. Yeah. Now this gives you a new formula, which is suppose you are given A given B, and somebody tells you to find B given A. Yeah. Now there is a direct formula for doing this, which is yeah. So yeah, this is just an observation. This is just an extension of what we said earlier. Okay. Yeah. So another interesting thing that this gives you is this way. This gives you a way of finding the probability of an event. So how does it do that? So suppose you have an event A, yeah, and it's a very complicated event. Okay, we want to subdivide the event into disjoint parts. Okay, so suppose we have a subdivision of the sample space. So B1, B2, B3 are a partition of the sample space. So you have you don't have a subdivision of A, but you have a subdivision of the entire sample space. Yeah. So that is B1, B2, B3. And then probability of A you can actually subdivide into A intersection B1, A intersection B2, A intersection B3. Why is this true? This is true because each of the sets are disjoint. So these are disjoint sets. Okay, so you can use simply additivity of probability and you can say this. And given this, then again you can use conditional probabilities. It will expand like this. Yeah. So probability of A is probability of A given B1 into probability of B1, A given B2 into probability of B2, and A given B3 into probability of B3. Yeah. So if you are given the conditional probabilities, yeah, of A conditioned on each elements of this partition, you can actually compute the probability of it. And this is a very useful formula. Okay, we will see a few instances where this will become useful. Okay, so that is enough formula. So let's again see a few examples. Okay, so that you are clear. Okay, so let's say you have 5 red and 2 green balls. Okay, these are indistinguishable balls. You have 5 red and 2 green balls in a box, and so you are taking a random ball and yeah, taking it out, and then you are putting back a ball of the other color. Okay, and just taking a random ball, putting back a ball of the other color, and then a second ball is drawn. Yeah. So what is the probability that the second ball is red? Yeah. So let's call this event A. Let's call this event B. Yeah. So yeah, what do you think the probability of B is? Yeah. How do you find the probability of B? Can we use the total probability law? Any ideas? So the question is clear. So you have a box. Inside that there are 5 red and 2 green balls. You are picking a random ball. Yeah. And I'm just throwing it out and putting back a ball of the other color. So if I pick the red ball, I'll put back a ball of the green color. If I pick the green ball, I'll put back the color, ball of the red color. Yeah. Now, yeah. So now what is the probability of B? What is B? What that if you draw it a second board, then it is red. Yeah. So yeah, please speak out if you have an idea how to solve this.
So we can start by considering two cases. If the random ball that I picked out was blue, so what will be the probability that the final ball will be red? And then another case too, in which the random ball I picked out was red, and then compute in that case. And so because these two events will be mutually won't have any overlapping events, so we can simply add it to get the total multiply to get the total probability.
Okay. So let me just write it down whatever you said. Okay. So let A1 be the event. Yeah. So A1 is the event that the ball that you first picked. Okay. Is red. And A2 be the event. Let's call this AR. Okay. And AG be the event that is green. Yeah. So AR and AG, AR union AG is sample space. Everybody agrees? Yeah. And they are disjoint. Yeah. And what does the total probability theorem says? So the total probability theorem says that if you want to compute the probability of B, yeah, probability of B is equal to probability of B given AR into probability of AR plus probability of B given AG into probability of AG. This is what the total probability theorem says. Yeah, so AR and AG is a partition. So if you remember, is there a question? Yeah. So B1, B2, B3 is a partition. So here instead of B's we have A's. Okay, A1, AR and AG is a partition, and we want to compute the probability of B. So you just use this formula. So is it easy to find the probability of B given AR? Suppose the red ball was picked initially. Yeah. Then I have replaced the red ball with a green ball. So now there are 4 red balls and 3 green balls. Yeah. So suppose AR happened. Suppose AR happened. Then there are 4 red and 3 green balls, right? And so what is the probability of B given AR? So B is basically second ball is red. Yeah. So there are 4 red balls out of a total of 7 balls. So this is 4 by 7. Yeah. So suppose AG happened. Yeah. If AG happened, what happens? So there are only 1 green ball and 5 red balls. Sorry, 6 red balls. Yeah. So probability of B given AG is going to be equal to, so B is second ball is red, so it will be 6 by 7. Yeah. So now we can compute the probability of B. So this quantity is equal to B given AR is 4 by 7. What is probability of AR? The first ball picked is red.
Sir,
Yeah.
sir, you are calculating the probability for red balls. Sir, in it has to be 3 by 7 and 1 by 7.
Sorry, you are having a problem with this.
Yes, sir. Sir, the B event is for the green balls, no? You are actually calculating for the red
This
balls.
is B.
Okay. Sorry, sir. I
Yeah, so
thought.
yeah, please go through it. Like, yeah, I mean, just yeah. So what is the probability of second ball is red? That is B. Yeah. So yeah, I mean, I'm just applying total probability law here. Yeah.
Okay, sir. Sir, I was confusing with the red balls. Okay, sir.
Okay. So yeah, there is AR happened, then this is the probability. And then if you look at the probability of AR, so what is the probability of AR? That is the first ball was red. The first ball was red is 5 by 7. Yeah. And yeah, B given AG. So B given AG is 6 by 7 into what is the probability of AG? So yeah, initially there are 5 red and 2 green boards, so that is 2 by 7. Yeah, is that correct? Yeah, so okay. So I guess so yeah, it will just calculate out the answer. Fine. So we just understood what yeah, total probability theorem is, and yeah, sometimes it is very useful because sometimes it's very useful to condition on an event. When you conditioned on this event, AR and AG, it is very easy to calculate the probabilities of B. Yeah. So we could compute the conditional probabilities easily, and then you could use the total probability theorem to add up to get probability of B. Yeah.
Sir, how these events are disjoint?
How
When we
is
are
AR
applying
and
the
AG disjoint? Is that the question?
yes, sir.
Okay. So can AR and AG happen together? Can the first ball picked be together be red as well as green?
No, sir.
Yeah, so that's why this is disjoint. Make sense? So,
No.
yeah, so that's what not just they are disjoint, but the union of them is a sample space. That's also important. Okay. So both these things are important. Okay, so we found so typically when you work with this conditional probabilities, yeah. So you kind of draw a picture. Yeah. So what will you will do is so first you pick the a board. Yeah. So let's have the two events corresponding to that. So this is AR and AG. Yeah. And suppose AR already happened. Yeah. Then the second board can be red or green. So those are these two elements of the tree. And the number you put here is the probability of the second ball is red given the first ball is red. Yeah. Similarly, this is the probability, this probability is the probability that the second ball is green, G2 meaning second ball is green, given the first ball is green. So green in the first place. Yeah. So yeah, so whenever you talk about conditional probabilities, it is better to draw the conditional probabilities in terms of this tree. So the first is the first choice, and then you have the second choice, and the edges of this tree are going to be denoted by these conditional probabilities. Okay, and it's good to remember this tree because it will make lot of calculation very simple. Yeah. So for example, this particular number is you are just multiplying out this particular number and 4 by 7. So if you draw this tree, it's very easy to do this calculations. Okay. So yeah, this tree will come up in multiple places. So let's see one example. Yeah. So what does the X number represent? So suppose we keep doing this 3 times. I picked a ball. Yeah. I threw it out and put a ball of the opposite color. Again, I picked a ball of the opposite color. Again, I picked a ball, threw it out, put a ball of the opposite color. I do it 3 times. So there are 3 levels in the tree. Yeah, corresponding to the first choice, second choice, and the third choice. Okay. So so we want to, yeah, what is the numbers x, y, c? I have to put in the, sorry. Yeah. So what are the numbers x, y, c I have to put in the tree? Yeah. So x represents the first choice. Yeah, that is the probability of the first board. Yeah. So this is A1. A1 is the probability of first board. Let's say is red. Yeah, and this will be equal to x. And what do you think y represents? Yeah, so let's say the left side means red and the right side means green. So what do you think y represents?
First ball is red, second ball is green.
Yeah. So I mean x has already happened. Yeah. So that is second ball is green, conditioned on first is red. Yeah. So you have to first go the red way and then go the green way. That's what y is. And what about C?
Again, red.
Again red, but what is the conditioning on?
What is this? So please repeat.
Yeah, so what should I write here? It is something conditioned on something, no? So you are saying this is third board is
Yes.
red because in the last it is going to its left. So what should I condition on?
Green ball, second green ball.
Only that?
Intersection of that
First
first
is
is
And
red.
red and
first is
second is
red.
green.
Yeah.
First is red, second is green, and third is.
First is red. Yeah. And
Second is
second
green.
is
Green.
green. Yeah. So the important thing is, suppose you take the probability written here and the probability written here, they should sum up to 1. So 4 by 7 plus 3 by 7 is 1. Yeah. So each time we are kind of subdividing the previous probability. So if I want to compute the probability of C, there's a very simple way of doing it. So sorry, the probability of if I want to compute the probability of the first is red, second is green, and the third is red. How do I compute it? In terms of x, y, z? Yeah. So now I just need to multiply out these numbers.
X into Y into Z.
Yeah. So now I can look at all the possibilities. So there are 8 possibilities, right? So I can easily compute the 8 possibilities by just going down that path in the tree and just multiplying out those conditional probabilities. Okay. So yeah, this tree is very useful. So if you write your probabilities in terms of this tree picture, the conditional probabilities formulas and calculations becomes very simple. Okay.
Excuse me, sir.
Yes.
Sir, when we multiply like this, it means that they are not relating and they will not affect. Is it correct? Each
No,
other?
we are just using the conditional probability formula. So what are we saying? So let's say A1 is the event. So A1 is the event that the first is red. Yeah. And B, let's say B2 is the event that the second is green. And C1 be the event that the third. So okay, I'm just inconsistent with the notation. I should use different notations actually. Let's call this PQR. So this is P, this is Q, this is R. So third is red. Yeah. What am I interested? I'm interested in the probability of P intersection Q intersection R. Is that right?
Yes, sir.
How do you compute this? So by conditional probability, we know that this is equal to the probability of P into the probability of Q intersection R conditioned on P. You agree? Then again we can expand this into probability of P into the probability of, so again we can have a, so this conditioned on P is also a probability distribution. So I can now say it is probability of Q conditioned on P into probability of P intersection, just a second, probability of, so yeah, P intersection Q intersection R, sorry. Just a second, I'm just confusing. Q P into probability of A given B. Yeah. So Q intersection R given P, and yeah. So this conditional probability will be probability of Q conditioned on P into the probability of R conditioned on P intersection Q. And what is this number? This number was our X. This number was our X. And conditioned on X, what is this number was our Y. Yeah, so I'm just using the conditional probability rule.
Okay, sir, I got it.
Okay. So, I mean, this tree is a way of visualizing the conditional probability use as a picture. That's all. Okay. So let's continue. Okay. So yeah, we already answered. Yeah. So yeah, I mean, we will go through this
what
question.
Was the answer? So sir, what was the answer? P of A1.
What was the answer for?
So this is the probability of X represents.
Oh, what is the probability of X you want to know? Yeah, so yeah, X is how much? So A is A1 is the first ball is red. How many balls were there? There was I mean 5 red and 2 green balls. So this is 5 by 7. Right?
Yes, sir.
Yeah, so, no, so this question was just to understand the tree and how tree. That's all. Okay. So how to apply the the formula by looking at the tree. That's all. Okay, so yeah, so now we can come back to the Monty Hall problem. Okay, so I want you to try to solve this yourself. Okay, so we won't be looking at the solution right now. Okay, so we'll be looking at it later, but I want you to give it a try. Okay, now how do you approach this problem? So there is some randomness. Okay, so let's say initially the one car and the two goats are randomly assigned. Yeah, and yeah, you picked one door and the host showed the door in which the goat was there, and should you switch or not? So you need to decompose these problems into A, B, and C, and then apply conditional probability and yeah, justify why switching is better or sticking with the earlier choice is better. Okay, so you need to think about it yourself and make the argument. You need to decompose the problem and what are the A's here, what are the B's here, what are the C's here. Yeah, and then you can draw the tree and make the argument. Okay, so I want you to do this exercise. Try to do it exercise yourself. Okay, so we'll be looking at it in the next class. Okay, so we'll continue the lecture. So yeah. So yeah, once we know about conditional probabilities, the next thing is independence. Yeah. So suppose you have thrown this dice.
Excuse me, sir.
Yes.
Sir, before we move on to this topic, so there was a second question to the previous problem.
Okay.
Yeah.
which is
our question for red and green balls. There was a second question. Like, could you scroll up a little? Yeah.
Yeah.
This
So
second.
what is the probability that the first ball was red given the second ball was red? Yeah, that's a great question. Yeah. So how do you do that? It's kind of the probability of AR given BR. Yeah. But now that is not easy to calculate with this tree. Yeah. So let's look at that. How do you do probability of AR given BR? We could calculate BR given AR very easily, right?
We can use Bayes' theorem for finding prior probability.
So we already had a way of flipping the conditioning. Yeah, so we just wrote it down above. I thought we wrote it down above. So this is equal to probability of AR intersection BR, yeah, into, do you remember what the formula was? Yeah, so we just wrote it down. Yeah, so this is probability of AR intersection BR divided by probability of BR. Yeah, and we just need to multiply it by probability of AR. So remember this formula. Yeah. So yeah. So B given A is probability of AR divided by probability of BR. Is that fine?
So I can't follow.
No, sir.
Yeah, sorry. I think I got confused. So yeah, for doing that second part, you need a Bayes rule. Okay, so just a second. So we want to compute the probability of AR given BR, right? So let's write down the formula. This is the probability of AR intersection BR divided by probability of BR. Yeah. Now, yeah. So how do you compute AR intersection BR? So can we compute AR intersection BR? So AR intersection BR is basically this probability, right? Yeah. So it is 5 by 7 into 4 by 7. We just need to multiply out the conditional probabilities. So that is equal to 5 by 7 into 4 by 7. This is very annoying. Sometimes the touch doesn't work properly. Yeah. So we are interested in computing AR given BR. So AR intersection BR is 5 by 7 into 4 by 7. And the probability of BR is, yeah, the second ball is red, is we already computed it, which is, yeah. So the probability of B is, yeah, we already computed it to be this number. So this number we can go in the denominator. Yeah, it's a two-step process. First, you need to compute the probability of B. Yeah, and then you need to, yeah, the numerator is easy to calculate from the picture. Is that fine? Yeah. So yeah, this is how it works out in the total probability. Yeah. Okay, so yeah, so let's continue. So is there a question?
Yes, sir. Sir, can you just explain me the difference between a mutually exclusive event and disjoint events?
Mutually exclusive and disjoint events. So this is not related to this particular slide, no? Yeah.
No, sir, it was means it's a very basic, so I thought to ask you.
Yeah. So I as far as I remember, it's the same thing. Yeah. So yeah, exclusive and disjoint events are the same thing.
Okay, sir.
Yeah. So suppose you have this throw of dice. So you are doing throwing the dice twice. Okay. So you have 6 things and 6 things here. Yeah. So yeah. So you have 6 things here and 6 things here, and then you want to yeah. I mean, suppose what is the probability of the first dice is 5 conditioned on second dice is 3. Yeah. So do you think whatever happened for the first dice depends upon the second dice? Yeah. So yeah. So if you remember, the probability space was uniform. Yeah, and it was constructed as a product of two probability spaces. Yeah, the first dice was some independent you are throwing, and second dice doesn't depend upon the first dice. Yeah. So this is same as the probability of the first dice is 5. So whenever you have such kind of a situation, it is called independent. That is, probability of A given B is equal to the probability of A. Okay. So yeah, the events A and B are independent if probability of A given B equal to probability of A. So this also implies the other way also. Probability of B given A is also equal to the probability of B. Yeah. So whenever this situation happens, it is called independent events. Yeah. So yeah. So whenever A and B are independent, so another inequality that equation that you will get is the probability of A intersection B is probability of A given B into probability of B, right? But A given B is the same as the probability of A. So this is probability of A into probability of B. Yeah. So yeah. So A and B are independent if A given B is same as the probability of A. And when that happens, yeah, probability of A intersection B will be just probability of A into probability of B. Okay. Typically, this happens when you are just repeating the same experiment multiple times independently. Yeah. More specifically, that Bold's case, things are not independent. Yeah. I mean, what happened, what Bold you saw in the first round dictates the probability that will happen, what will happen in the second round. Yeah. So suppose you write down the tree for this for this dice throws. Okay, so you have the first experiment. There are 6 outcomes for the first experiment. 4. Yeah, so this corresponds to the first dice being yeah. This corresponds to the first dice being 1 to 6, and then again you have 6 experiments, 6 outcomes, 2, 3, 4, 5, 6. Yeah, so this also has 6. Yeah. Now the probability of the first dice being equal to 1 is 1 by 6. Yeah. Everybody agrees that all these numbers are equal to 1 by 6. Now, conditioned on the first event, what is the probability of second dice being 1? That is also 1 by 6. Yeah. And in fact, all these numbers are same as all these numbers. Yeah. So it's very important. So if you look at the earlier picture, yeah, the numbers here depend upon the previous numbers. The numbers here and the numbers here are not the same in the tree. But when things are independent, the numbers here, the numbers in this part of the tree would be the same as this part of the tree. Okay. So is that clear what independence means? So if you have a question, please speak. So I think we are already over time. Okay, sorry. Is this? Yeah, it's almost 10:30. I think we are already over time. So what did we do today? Okay. So we looked at what conditional probabilities are. We looked at what conditional probabilities are. We looked at the formula, how to compute them, right? Secondly, we looked at the total probability rule. Yeah? So if you have a partition of the sample space, you can actually compute the probability of an event by looking at, adding up the probabilities according to the intersections. Yeah? So then we looked at a way of organizing these conditional probabilities as a tree, yeah, and that helped us to work out the formulas easier. Yeah. And yeah, so then there is this question. This is kind of a homework for you. You should try it yourself. Okay, how do you reason out that switching is better than don't switching, or the other way? Okay, whichever you think is appropriate. Yeah. And we also looked at the definition of independence. Independence just means that if you just work out the tree, the probabilities in the next level of the tree does not depend upon the first level. Okay, like it is not like this. So here the probabilities here 4/7 and 3/7 is different from 6/7 and 1/7. So yeah, so yeah, what happens to the second board depends upon the first board. But if you are throwing dice independently, this doesn't happen. Okay. Yeah. So that's all for today's lecture. Yeah. If there is no questions, we have just 2 minutes. If there is no questions, I will end the class. Okay. So
Sir,
yes.
So we have a tutorial at 1, right? So would we be practicing questions in that?
Tutorial at 1? I'm not sure there's a tutorial at 1.
So, could you please look into it?
Yeah. So there are actually 2 probability courses. One is the undergrad probability course, and that is having a tutorial at 1.
Oh, okay, all
So
right.
this is the mathematics for computer science, probability and statistics course. For that, there's no tutorial slot allocated. Okay, but we will have a office hours tomorrow. So the schedule is given in the channel.
Okay, sir.
The general channel, you can see that event has been scheduled. So you can ask your questions. If you don't ask any questions, the TS will be solving some problems.
Fine, sir. Thank you so much.
Okay. And finally, there will also be a quiz, light quiz related to this lecture will be put out today. So you will have a time before Wednesday's lecture. Sorry, Thursday's lecture. You will need to finish that light quiz. Okay. So that's all for today. Okay. Thank you.